Have you ever stopped to wonder how the sound of your voice, this smooth, continuous wave of energy, gets understood by your phone? You know, a device that only really thinks in ones and zeros? How does the rich analog world we live in get translated into the rigid, step-by-step language of computers? Well, today, we're going to dive right into that. It's a really fascinating puzzle when you think about it. Our world is all about flow with infinite detail, but computers, they're all about definite, separate steps. There's no such thing as in between. So how in the world do we bridge that fundamental gap? That's the big question we're going to tackle right now. All right, so before we can build that bridge, we really need to understand the terrain on both sides. Let's get a super clear picture of these two very different worlds, the analog world we experience every day, and the digital world our devices call home. And this, right here, is the perfect way to see the difference. On the left, you've got that classic analog clock. Its hand just glides, smoothly passing through every single possible microsecond. It's continuous. But the digital clock, it just jumps. 1 second it's 8:07, and then bam, it's 8:08. There is no in-between. It exists in these separate, distinct steps. That's what we call discrete. So to put a finer point on it, an analog signal can take on an infinite number of values within a range. Think of a dimmer switch for a lamp. You can slide it to be a little bright, a tiny bit brighter, or any one of the infinite points in between. It's a smooth, continuous spectrum. It's analogous to how things work in the real world. Okay, so if our world is analog, but our computers need something totally different, we're going to need a translator, right? We have to find a way to convert that smooth wave into those rigid digital steps. This is where we start building the bridge between these two worlds. And here's what's waiting on the other side of that bridge, a digital signal. So unlike that smooth dimmer switch, this is more like a standard light switch. It's either fully on or fully off. Or maybe, it has 3 settings, off, low, and high. The key thing is there's a limited, predefined number of states, or levels. There's absolutely no in-between. So how does this magic actually happen? Well, it's all handled by something called an analog-to-digital converter, or ADC. And you can think of it as a pretty simple 4-step process. First, it receives the analog signal like your voice hitting a microphone. Second, it samples that signal, basically taking thousands of little snapshots of it every second. Third, it quantizes. For each of those snapshots, it finds the closest matching level on its predefined digital ladder. And finally, it converts that level into the binary code the computer can actually use. Now, you might have noticed something kind of weird in that process. Why assign a measurement to the nearest lower level? Wouldn't it be more accurate to just go to the closest one, up or down? Well, it's all about consistency. By having one simple, predictable rule, like always round down, the system avoids confusion and potential errors that could pile up. It's a small trade-off, a tiny bit of precision on one measurement in exchange for perfect reliability across millions of them. So we've turned our smooth wave into a series of steps, and each of those steps gets a binary name. Let's take a closer look at what that binary name, the actual language of our computers, is all about. The most fundamental, the absolute most basic unit of all digital information is the bit. And a bit is just like that simple light switch we were talking about. It has only 2 possible states, off, which we call a 0, or on, which we call a 1. That's it. That's the entire alphabet for a computer. Okay, so one switch, that's 1 bit, gives us 2 levels. Not a lot to work with. But check out what happens when we add another one. Now we have 4 possible combinations. Add a 3rd bit, and we jump all the way to 8. You see the pattern here? Every single bit we add doubles our descriptive power. And this is where the exponential power of this whole system just blows you away. By the time you get to just 10 bits, 10 little switches, you're not dealing with 20 levels. You're dealing with 1,024 distinct levels. All of a sudden, you can represent that original analog signal with incredible detail. So the crucial takeaway here is simple. More bits means more levels, and more levels means way more accuracy. It's kind of like grading students. If your only grades are pass and fail, you're not getting a very accurate picture of their performance. But if you have grades from A+ all the way down to F, you can be much more precise. More bits just give us more grades to work with. This seems like a lot of work, right? All this capturing and sampling and quantizing. Why do we go through all this trouble instead of just using the original analog signal? Well, the answer is one of digital's greatest superpowers. You see, the big weakness of analog is something called noise. Let's say you send a signal that's exactly 2.5 volts, but along the wire, it picks up a tiny bit of electrical interference, let's say 0.2 volts of noise. Now the receiver gets 2.7 volts. And because any value is possible in analog, the receiver has no choice but to believe the signal is really 2.7 volts. The information has been corrupted. Okay, now watch what happens in the digital world. That same corrupted 2.7 volt signal comes in, but the digital receiver is a lot smarter. It has a list of valid levels, say 0 volts, 1.25 volts, 2.5 volts, and so on. It sees 2.7 and says, whoa, hold on, that's not one of my allowed values. So it simply snaps the signal to the closest valid level it knows, which is 2.5 volts. And just like that, the noise disappears. It's incredible. And this noise immunity isn't the only advantage. Digital signals are also way more efficient to send over long distances, they can be easily encrypted for security, and they often use up less bandwidth. It's a whole package of benefits that we get from this conversion process. All right, so the computer has received the clean, noise-free digital signal, it's done its processing, and now it has an answer. But that answer is still in the language of bits. We need one final step to make it useful to us back here in our analog world. And this is the job of the digital-to-analog converter, or DAC for short. It does the exact opposite of what we did before. It takes the computer's output, that stream of ones and zeros, and translates it back into a smooth, continuous analog signal that can power a speaker to make sound or light up the pixels on your screen to create an image. I mean, think about a digital clock at a train station. If the computer's internal brain just spat out 1,000, 1,000, that would be completely meaningless to a traveler trying to catch a train. The DAC is the magic part that interprets that binary code and turns it into the electrical signals needed to light up the display to show 808. It's that final, crucial bridge back to our reality. So that's the bridge that connects our two worlds. But it leaves us with a really fascinating final thought. As we add more and more bits for things like 4K video or high-resolution audio, our digital steps become so incredibly tiny that they mimic reality almost perfectly. So here's the question. In our quest for digital perfection, are we just on a long journey to become analog all over again? Something to think about.